Continuing on in this lecture series, we're going to move on to the Doppler equation. We'll talk about the specific parts of it and how they relate to one another. All right, so here's the Doppler equation. Again, it's going to look like a lot of math in this lecture, but the biggest point to pull out of this is how do each of these items relate to one another as they sit on either side of that equal sign or above and below the division part of it. It's going to be important to recognize if velocity of blood increases, what does that do to the Doppler shift? If the transducer frequency increases, what does that do to the Doppler shift? What does it do to the velocity of the blood? How does cosine of theta affect everything? So understand those relationships and you will be pretty good to go on the Doppler equation. So with the Doppler equation, we say that Doppler shift equals 2 times the velocity of the blood times the transducer frequency times the cosine of theta, all divided by the propagation speed. So fantastic to know that, but in the end what the machine is actually trying to figure out is the velocity of the blood. So as we shift things around mathematically, we now get velocity of blood is going to equal the Doppler shift times propagation speed divided by 2 times the transducer frequency times cosine of theta. As far as memorizing these, if you can memorize the Doppler shift equation, what it equals, you should be able to then rearrange everything mathematically, balancing out the equation to understand how velocity of blood is calculated. So we can kind of break down the Doppler shift equation a little bit more. As I had said before, it's going to be really a matter of how is all of this related to one another. So Doppler shift, velocity of blood, transducer frequency, and cosine of theta are all directly related. If one goes up, the other goes up. If one goes down, the other goes down. Those are all directly related as they sit on opposite sides of the equal sign. The 2 is going to be a constant. It's always going to be there. And the 2 accounts for the fact that there's a transmit and a receive Doppler shift. So the 2 is normal, always stays there. Propagation speed in ultrasound always equals 1540 meters per second as well. So propagation speed will never change for the purposes of ultrasound Doppler shift. So we're going to break down each part of the Doppler shift equation and kind of show you a little bit more about how those objects are directly related as they sit on either side of the equation sign. Again, you will not be asked to do any math on your tests, either in class or really on the boards, but you do need to be able to recognize if something doubles, then another number should double, and you should be able to multiply things by 2. Fairly simple in your head. So let's look at our example. The Doppler shift and blood cell velocity in this example, they are directly related. If the velocity doubles, then the Doppler shift is going to double. Same is true if the velocity is quartered, then the Doppler shift is quartered. So let's look at our example. We have that 8,000 hertz equals 2 times 246 centimeters per second, that's our velocity of blood, times 5 megahertz, which is our transducer frequency, times the cosine of theta, which is 0.5 in this case, divided by our propagation speed, 154,000 centimeters per second. The big part with, if you are doing math with these, is that you have matching units, so everything equates to the correct unit in the end. So here, the biggest part here is that we were talking about that velocity of blood was 246 centimeters. After doing the math, we get to 8,000 hertz. In our next example down, we have 123 centimeters. That is 1/2 of 246. So what do we expect to happen to that Doppler shift? We expect that to also be halved. 8,000 divided by 2, or by 1/2, gives us that 4,000. So you can see as this is halved, so is our Doppler shift. So let's break it down again for Doppler shift and transducer frequency. Again, we remember that these two are directly related, and we can see that again in our example. Doppler shift was figured at 8,000 hertz using the equation. Our transducer frequency is 5 megahertz. Drop down to our example, we reduce the transducer frequency to 2.5 megahertz, which is half of the 5. And as expected, our resulting Doppler shift is also half of what it originally was. so they are directly related. We could do it the opposite way if we switched this to 10 megahertz, leaving everything else the same. Our Doppler shift then would be 16,000 hertz. Another part of the Doppler shift frequency that is also directly related to Doppler shift is the cosine of theta. And this concept might not be as familiar with you, so hopefully we'll be able to explain it well in the next few slides here. So cosine of the angle between the ultrasound beam and the moving blood cells is cosine of theta. If we could always have parallel movement to our transmitted beam, we would get 100% accurate velocities measured. The problem is that the way that the blood vessels travel through the body, we're typically not going to get that parallel movement. So we deal with an angled movement. This is going to be less than 100% accurate velocity, but that's okay. We figure out how to deal with it. The other part of this is that any movement that is perpendicular to the ultrasound beam is not going to show any recordable velocity. So it's important that we keep that cosine of theta, or the angle at which we're measuring that blood velocity, that we want to keep it somewhere between 0 and 89, so we're not at that 90, ideally keeping it at 60 degrees at the most. Doppler shift is going to be directly related to the cosine of theta. If the cosine of theta is halved, then that Doppler shift is also going to be halved, just as we've seen in previous examples. So let's talk a little bit more about that cosine and how it relates to the angle of inclination and the direction of blood flow. So the cosine of theta is actually going to be figuring out this angle that's labeled A on this slide. If we can pretend that our transducer is up here and that this is our blood vessel, we want to figure out the angle between how the blood is moving and how the beam is coming in to that blood vessel. So we are figuring out this angle here. We can see it in our other example on the side here. As our ultrasound beam is coming into the blood vessel, we steer it a certain way. We have blood traveling this way. We want to figure out the angle of that beam coming in and the direction that the blood cells are moving. This is our theta angle. So when we do a theta cosine, it comes up with actually pretty rounded out numbers, and this is the number that we would fit into our equation. So again, we have our angle coming in of our sound compared to how it's hitting our blood cells, and this is the angle. We measure angles in degrees, and we can see down the list here 0, 30, and 60 degrees. These are really common stops for ultrasound machines. We then have 90 degrees, and then 120, 150, and 180. If you notice, 180 and 0 are both 1 and then a negative 1. 150 and 30, 0.87, negative 0.87. 60 and 120, 0.5, negative 0.5. And then our 90 gives us that 0. So again, 0, 30, and 60 are going to result in towards directions. 120, 150, 180 are essentially the same as 0, 30, and 60. They just provide negative numbers, which will give us away direction. And the biggest thing to remember, 90 degrees is perpendicular. We cannot figure out any Doppler shift when we are at 90 degrees. It just negates the whole equation. You can see that from our example column here. As we put a 0 in here, that makes everything on top 0 divided by the propagation speed, which will equal 0 hertz. The machine just can't figure it out. Doesn't think anything's going on. It's just the way the math works on it. As you plug in positive numbers versus negative numbers on the bottom, you're going to get those negatives and positives. When we talk about the inclination angle, we do say that we want you to stay at 60 degrees or less. 60 degrees is the same as 120 degrees. 0 degrees is the same as 180 degrees. It's just a matter of how that blood is traveling in relation to the angle of the beam coming out of the transducer. So remember that those are the same and that 90 is a no-go. So hopefully this slide will help to exemplify that even more. We have a blood vessel here with the blood flow traveling from the right of the screen to the left. As we put a transducer, if we could be 100% parallel with that beam, that would give us a 0-degree angle. Cosine of 0 equals 1. As we start to swing up and have to increase our angle here, we can go up to a 30-degree angle. Cosine of 30 equals that 0.87. This is still a positive shift because it's moving towards our transducer. As we switch to our cosine of 60 degrees, we get 0.5. Again, blood is still moving towards our transducer, so we stay in that positive 0.5 number. As we flip our transducer around and get to that perpendicular inclination, put that 0 into the equation, the whole equation kind of breaks down and gives us a 0 Doppler shift. We just can't do the math on that. Same is true then as we start to come from a different side. We can see cosine of 120, which is the same as 60, just on the negative side. The blood is still traveling right to left, which is now moving away from this transducer. So we get that negative number. As we move down, this is still a 30-degree angle, but it's still moving away from our transducer, so we get that negative 0.87. And then again, cosine of 180 puts us back parallel with the blood flow, but all of the blood is moving away from our transducer, so we're going to get that negative number again. And 180 is the same as 0. So a big takeaway on understanding the cosine of theta concept is that you will be able to determine how accurate the blood velocities that you are getting actually are. So yes, we do say that getting closer to 0, we're going to get that 100% accurate measurement. That's truly, truly what we should be striving for. In echo, almost all of your windows put you at that 0-degree angle of incidence, not even something that you guys really think about. However, for the rest of the body, when we're trying to look at blood velocity traveling through vessels, be it the legs or up in the neck, we can't get that 0-degree angle of incidence. So we manage by changing the angle. It's a very standard practice to go to 60 degrees because it's very attainable in most of the vessels in the body, and it's also repeatable. So 60 degrees is actually pretty much the standard that we will use in clinic ultrasound. The further we get away from 0, though, the less accurate our measurements are going to be. But again, 60 degrees is very standard now. It's something that we deal with. It's something that all of our lab values are based on when we're figuring out velocities and how they equate to disease. So this slide kind of shows us a little bit more about how that works. So A is going to show us an inclination that's probably closer to maybe like a 30 degrees, but getting towards that 0, that true angle of inclination. And we can see that we've got a nice high velocity on A. That is going to be more accurate than anything further away from 0. B, however, is probably showing us our typical blood value, or showing us our typical angle that we're showing coming in at the blood. So as you can see, B still has a nice high velocity, but it's going to be lower than what A is. It's just a matter of putting that 0.5 into the equation. It's just going to give us a lower Doppler shift. C then is starting to get a little bit closer to 90 degrees, and we are definitely over that 60-degree threshold. And so as we get closer to 90 degrees, we're going to start to get very inaccurate velocities. We can see on C that the velocity is nearly half of what A and B were. So this is very inaccurate, very much underestimating the true velocity. D then is just showing us an example that now that we've changed basically our position of B, that the blood cells are perceived now as moving away from the transducer, and that those would be displayed as negative Doppler shifts. As I had mentioned on an earlier slide, that 2, that is always going to be there. That 2 will not change, does not change to another number, it is just there. So you'll need to know that to make sure to put that into your equation when you're memorizing this Doppler shift equation. And it accounts for the fact that there's actually two Doppler shifts occurring while the transducer is transmitting, and then again while it's receiving sound. The last part of the Doppler shift equation is just to memorize that propagation speed is the same. It's the same as it's always been for soft tissue ultrasound, 1540 meters per second. Then another note on here, hertz versus centimeters per second. The ultrasound system is going to measure the frequency shift, but reports the velocity of blood. So the machine is actually figuring out the Doppler shift the whole time that we're using our pulse wave to look at how blood is flowing. In the end, though, it's going to report to us what the velocity of blood is. The velocity of blood is clinically more significant than us getting information from the machine saying, oh, it's a 3000 hertz Doppler shift. Like, that doesn't mean a whole lot to us. So the machine calculates then the velocity of blood for us because that's what's significant to us as we make our clinical diagnosis. All right, so it's time to test yourself. Biggest thing from this chapter, we're going to need to know the Doppler equation, so memorize that equation, and know the relationships of everything between Doppler equation or Doppler shift and how that relates to the velocity of blood, to the transducer frequency, and to the cosine of theta. Understand why the 2 is in there, and memorize what propagation speed is. Those are going to be your big parts on Doppler equation. The other part that you really will need to understand is why 0 degrees is the best, why 90 degrees is the worst, and why we typically use a 60-degree inclination. Again, echo, it's going to be a little bit different for you guys in that almost all of your windows give you that awesome 0-degree angle of inclination. General sonographers use more of a 60-degree because it's easier to attain and repeatable. So number 1, what does the 2 stand for in the Doppler equation? Number 2, what is the propagation speed in the Doppler equation? Number 3, the Doppler shift using a 12 MHz transducer is 8000 Hz. The sonographer switches to a 3 MHz transducer. What is the Doppler shift? Again, this is a math problem that you should be able to do in your head or easily on paper. You will not be allowed calculators. These are the type of math problems that you will need to be able to complete. Number 4, the Doppler shift is 3000 Hz and the velocity of blood is calculated at 154 centimeters per second. The sonographer samples in a stenosis and the Doppler shift is 6000 Hz. What is the velocity of the blood? Number 5, which cosine of theta angles are the most accurate? Which cosine of theta angles are standard practice? And which cosine of theta angles should we never use? Number 6, again, what questions do you have about this lecture?